Welcome to the Deep Dive, the show where we take the most complex and, frankly, fascinating source materials and distill them down into the knowledge you really need to be well-informed.
Today, we are definitely on the frontier. We're taking a journey into neurological science, specifically into a field that's all about how the brain sustains itself, how it adapts, and maybe how it can even repair itself after damage.
That's right. And we've got a pretty hefty stack of sources in front of us. Everything from, preclinical research reports and pretty dense peer-reviewed articles on neurotrophic factors, all the way to regulatory documents that define the really strict boundaries around what are called research-grade compounds.
And our focus for this deep dive is a compound named P21.
P21, yeah. It's a peptide that's been generating a lot of excitement, at least in research circles, because its potential, its purported potential is to radically influence neuroplasticity and the brain's resilience.
It's a very, very specialized area of study. You're often dealing with these tiny fragments of naturally occurring growth factors. The language can get highly technical, but the implications, if these early findings ever translate to humans, they're just vast.
Right. And that's why our sources are so important today to ground this discussion. We're focusing purely on the preclinical data, so lab and animal studies, and the absolutely necessary scientific and regulatory context that goes with it.
Exactly.
So our mission today is crystal clear. We're going to dissect the science behind P21. We're going to explore its really surprising origin story, which you can trace back to this powerful natural compound. We'll break down how it's supposed to work.
Its mechanisms of action.
Right, the mechanisms, which, and this is the wild part, seem to involve literally removing the natural brakes on brain growth. And then, crucially, we have to establish its strict classification as a research chemical. We're going to jump right into the deep end here and understand what the lab reports are actually suggesting.
And that context is absolutely foundational. P21 is it's highly intriguing because of its potential to modulate how the brain heals, adapts, and learns, especially in response to injury or neurodegenerative stress.
But there's always a but.
There is always a but. That potential is, for now, confined entirely to the preclinical and laboratory settings. And understanding that gap, the massive gap between a promising lab result and a viable, safe human therapy, that's paramount for today's discussion.
Okay, so let's start at the very beginning. Let's unpack this thing. To really define P21, we have to trace its lineage. Where does this synthetic peptide actually come from? What was the initial goal behind engineering it in the first place?
Well, P21 is really a classic example of what you'd call targeted drug development. It's a synthetic peptide. That means it was meticulously designed and created in a laboratory. It's not something you just extract from a plant or an animal.
Right, it's built from the ground up.
Exactly. And its identity is directly tied to a previous research compound, one called P021. And P021, in turn, was designed based on a much, much larger naturally occurring molecule in our bodies called ciliary neurotrophic factor.
Ciliary neurotrophic factor. Okay, so that's CNTF for short.
So CNTF, yes. You'll hear that a lot.
So we've got this lineage. CNTF, which is the natural stuff, led to the creation of P021, which then inspired P21. So let's start with the grandfather of the group, CNTF. What is this ciliary neurotrophic factor, and what does it normally do in the nervous system?
CNTF is a member of the cytokine family, which, are just signaling molecules. Think of them as messengers. And its primary function is robustly neurotrophic.
Neurotrophic, meaning brain growing.
Essentially, yes. It means it supports the growth and, just as importantly, the survival of neurons. It's absolutely vital during development, helping to guide how neural cells and glial cells differentiate and form the structure of the nervous system.
Okay, so it's a construction foreman when you're building the brain. What about in adults?
Even in the adult nervous system, it acts as a critical maintenance and protective factor. It's particularly relevant in things like peripheral nerve repair and in maintaining the health of the spinal cord. It's kind of like a resident medic, always on call to support and protect the nerve cells.
A natural emergency response system for brain and nerve cells.
Yeah.
That sounds incredibly powerful. So, given that, why did researchers feel the need to move past the full CNTF protein? Why go to all the trouble of engineering a tiny fragment like P21 if the original is so great?
That is the core engineering problem they faced. CNTF is incredibly powerful, you're right, but it's fundamentally impractical for therapeutic use in its native, full-sized form, especially when you're trying to treat something inside the central nervous system, like the brain.
Impractical how?
Well, there are three major hurdles. The first and most obvious one is just size. The full CNTF protein is large, biochemically speaking. It simply cannot effectively cross the biological barrier that's designed to protect the brain.
The blood-brain barrier.
Exactly, the blood-brain barrier. So you can inject CNTF systemically, into the bloodstream, but very, very little of it, if any, will actually reach the neurons inside the brain that you're trying to help.
So you inject the full protein, it just kind of circulates around the body, gets metabolized, and never makes it to the target site. It's like having a key for a door, but the key is the size of a car.
That's a great analogy. The door is just too small. The second issue is stability and half-life. Large proteins, especially signaling molecules like CNTF, they tend to have very short half-lives in the body. They get broken down by enzymes very quickly.
Which means you'd have to take it constantly.
It would necessitate extremely frequent, maybe daily or even multiple times a day injections, which makes any potential treatment completely impractical and incredibly expensive.
Okay, that makes sense. And you mentioned a third hurdle, something immunological.
Yes. The third is immunogenicity. When you introduce a large foreign or even a bioidentical protein into the body repeatedly, you significantly increase the likelihood that the immune system will recognize it as an invader.
And it attacks it.
It mounts an antibody response against it.
Yeah.
And that does two things. One, it neutralizes the protein before it can even do its job. And two, it can potentially cause systemic inflammation or even dangerous allergic reactions. Researchers needed something small, stable, and stealthy, something that flies under the immune system's radar.
So P21 and its precursor, P021, were basically born out of necessity. They're a way to deliver the message of CNTF, that survive and grow message, without bringing the large problematic messenger molecule along for the ride. That's a genius piece of biochemical engineering.
It really is. What they did was identify the specific, highly active region within that huge CNTF protein that's actually responsible for binding to and activating the required receptor complex.
So they found the business end of the molecule.
Precisely. This receptor complex is primarily composed of something called CNTF receptor alpha and two signal transducing subunits, GP130 and Li-afar. Don't worry about the names. The point is, P21 is a tiny peptide fragment, often just an 8 amino acid chain, that is designed to perfectly mimic the three-dimensional shape of that active site.
So it doesn't need to be the whole key. It just needs the precise tip of the key that fits into the lock and turns it.
That is a perfect metaphor. And because this fragment is so incredibly small, typically less than 1 kilodalton in molecular weight, it achieves two critical things. First, vastly improved bioavailability. And second, the ability to potentially navigate that blood-brain barrier. Though, as we'll discuss later, they have a very clever way of maximizing that brain penetration.
Before we get to P21 itself, tell us a bit more about P021. It's the direct precursor, the one that really laid the foundation. What were the specific successful results they saw in animal studies that made them say, aha, this fragment approach really works?
The P021 research was exceptionally encouraging. It was primarily conducted in animal models of neurodegenerative conditions like Alzheimer's or Parkinson's models, and also in brain injury models.
And what did they see?
They saw clear, measurable evidence of improved cognitive function. For instance, in memory tasks like the Morris water maze, which is a classic test for spatial learning in rodents.
That's where they have to find the hidden platform in the pool of water, right?
That's one. Animals treated with P021 demonstrated significantly reduced latency. That means they found the hidden platform much faster. And they showed greater retention of the platform's location over time compared to the control group. This directly suggests improved spatial learning and memory consolidation.
Wow, so that's moving way beyond just keeping neurons alive. That's actually making them perform better at a complex task.
Exactly. It's a functional improvement. Furthermore, P021 was shown to have a dose-dependent effect on stimulating new neuron formation neurogenesis, particularly in the hippocampus.
And the hippocampus is the brain's memory center.
It's absolutely critical for forming new memories. And perhaps most importantly, it was confirmed to increase levels of brain-derived neurotrophic factor, or BDNF, which we're going to talk a lot more about. The P021 research basically verified the fundamental concept that a small, stable, engineered fragment could replicate the powerful neurotrophic and cognitive benefits of its massive parent protein, CNTF, without all the drawbacks.
Okay, so P21 is essentially the refinement of that. It's the next generation of P021, aiming for what may be better stability or a stronger bond with the receptor. So where does P21 stand today in terms of scientific verification compared to its predecessor?
P21 builds on the structure and the mechanism established by P021. It's often referenced in these research chemical circles as having a slightly optimized structure. But the critical distinction is that P021 had a slightly longer run in foundational, published, peer-reviewed studies. P21 is the newer compound.
So more cutting edge, but less proven.
Exactly. While it is thought to work in a very similar way, the direct, dedicated, published studies on P21 specifically are less numerous than those detailing P021. It really represents the current edge of laboratory investigation. So, very high potential, but with less of a verified public paper trail so far. It remains firmly a research stage compound, not a finalized product with a huge body of independent data.
That is a really necessary clarification. So they're in the same family, they have similar goals, but the specific behaviors, and especially the long-term implications of P21, are still very much under active investigation in the lab.
Precisely.
Okay, now we get to the core of all the excitement. This is where it gets really interesting. We need to move from what P21 is to how it works, the precise actions that make researchers so interested in its potential. You mentioned BDNF a moment ago, brain-derived neurotrophic factor. You said it's central to P21's proposed effects. Before we get into the 4 proposed actions, can you just fully define BDNF for us? Why is it so often considered the master switch for brain health?
BDNF is, well, it's arguably the most critical neurotrophic factor in the adult brain. While CNTF, its ancestor, is very protective, BDNF is the molecule that's really responsible for active growth, for structural maintenance, and for the efficiency of communication between neurons.
Okay, so if we're using an analogy, say the brain is a garden.
Right.
If CNTF is the solid foundation and maybe the irrigation system that keeps things from dying, what's BDNF?
BDNF is the premium specialized fertilizer. It's the stuff that ensures the plants, the neurons, are not only alive, but that they are thriving, growing strong, and becoming densely interconnected with each other. It promotes branching and complexity.
So it's not enough for a neuron just to survive. You need BDNF to ensure it's performing at a high level and staying flexible.
Absolutely. Higher levels of BDNF are very strongly correlated in both clinical observation in humans and preclinical models with enhanced synaptic plasticity.
And synaptic plasticity is just the ability of the connections between neurons to get stronger or weaker, right? That's how we learn.
That is the biological substrate of learning and memory, yes. Furthermore, robust BDNF signaling is crucial for mood regulation and for making the brain resilient against all kinds of stressors, whether it's psychological stress, inflammation, or an early-stage injury.
And low BDNF.
Low BDNF is often implicated in various cognitive declines, in mood disorders like depression, and in slower recovery from brain injury. So any compound that can reliably and safely boost the body's own endogenous BDNF levels is automatically a huge, huge focus for research.
That sets the stage perfectly. So our sources outline 4 main hypothesized actions where P21 is believed to influence the brain, all based on these preclinical findings. And these mechanisms show a really sophisticated level of biological targeting. Let's break down the first 2.
The first one is the one we started with. It's heritage from CNTF. It is promoting neuron survival and repair. Because P21 is a fragment that activates the CNTF signaling pathway, its most direct function is to enhance the survival signals that keep existing neurons functional.
Especially when they're under stress.
Exactly. When they're exposed to biochemical stress, like excitotoxicity from too much glutamate or inflammation, it binds to and activates that GP130 component of the CNTF receptor complex. And that sends a powerful stay alive and repair yourself message into the cell's nucleus.
So it's like it's activating the inherent defensive mechanisms of the neurons. It's making them tougher, harder to kill off.
Precisely. It's defensive support. But the second action is where the proactive, almost revolutionary aspect of P21 research lies. It's the belief that it blocks brake signals that limit growth. And this centers on inhibiting another factor called leukemia inhibitory factor, or LIF.
This is the concept I find so compelling and honestly a little counterintuitive. The idea that the brain has built-in brakes on its own growth and repair. If your brain is damaged, why on earth would it naturally limit its own ability to fix itself?
It's a crucial area for speculative research, but the leading hypothesis goes something like this. LAF is a natural component of the brain's microenvironment. And while it has roles in inflammation, its main function in this context seems to be as a regulator or a damper on stem cell differentiation.
So it keeps things in check.
It keeps things quiet. The adult brain contains neural stem cells, but they are typically kept in what's called a quiescent state, a resting state. LAF is part of the signaling cascade that maintains that quiet, non-dividing status. It actively prevents those neural stem cells from differentiating and creating new, specialized neurons.
So LAF is essentially a quality control mechanism. It's making sure the brain maintains stability rather than undergoing continuous, potentially chaotic growth all the time.
That's the leading hypothesis, yes. Constant, uncontrolled neurogenesis could be biologically very expensive in terms of energy or perhaps even structurally disruptive to existing stable neural circuits. So the body evolved these complex systems like LAF signaling to manage the pace of new neuron creation. It prioritizes stability over plasticity in the adult brain.
And P21 messes with that system.
P21 is believed to directly inhibit the signaling of LA. By doing so, it effectively removes that natural stop signal.
It takes the foot off the brake. And what is the observable result of removing this brake signal in a lab setting? What happens?
The observable result is a significant increase in an environment that is favorable for neurogenesis. When IF signaling is inhibited, it basically opens the door for those quiescent neural stem cells to wake up and start differentiating into mature neurons. Preclinical models indicate that P21 can effectively shift that balance, creating a pro-neurogenic environment, particularly in the hippocampus, that structure's so deeply involved in learning and memory.
So this mechanism, the ability to selectively turn off a natural growth inhibitor, is what really separates P21 from simpler neurotrophic approaches that just say add more fertilizer.
That's right. This isn't just adding fertilizer. This is also removing the weeds and tilling the soil to prepare it for new growth.
That is profound. I think we need to linger on the implications of that for just a moment. If this research on P21 eventually proves that we can reliably and safely turn off the LIF brake, even temporarily, it suggests that the adult brain has this enormous untapped regenerative capacity, just waiting for the regulatory system to get out of the way.
It raises huge philosophical and biological questions about the balance between stability and plasticity. The incredible stability of the adult brain might be a direct function of these inhibitors. But P21 suggests that by temporarily suppressing them, we might be able to access a period of increased plasticity and repair that's more reminiscent of what you see in early life.
But it also raises the big safety question.
It does. It raises the long-term question. What are the consequences of continuous LIF inhibition? Does that break exist for a very important reason related to long-term stability or, for example, tumor suppression? Those are the critical questions that future studies must address, and they are precisely why P21 remains strictly in the research realm today.
Absolutely fascinating. Okay, let's move on to the third proposed action, which ties directly back to our earlier discussion. P21's confirmed ability in preclinical settings to boost BDNF levels.
This is a beautiful synergistic effect. While the CNTF pathway activation is about survival and the LIF inhibition is about creating new neurons, P21 also significantly upregulates the production and release of BDNF.
The premium fertilizer.
The premium fertilizer. And this is critical because BDNF then amplifies the effects of the other two mechanisms. BDNF enhances the survival and resilience of the newly formed neurons, it improves the connections between existing neurons, and it basically acts as a positive feedback loop for overall brain health and function.
So we're back to the fertilizer analogy, but now we understand it's not just sprinkled on from the outside. P21 is actually increasing the garden's own internal production capacity for this stuff.
Precisely. And this BDNF boost has another critical secondary role that's mentioned in the source material: neuroprotection against the buildup of harmful proteins.
Oh, like the kind you see in Alzheimer's disease.
Exactly. The source material notes that BDNF helps regulate specific enzymes, such as those involved in the processing of amyloid precursor protein. In animal models of neurodegeneration, P21 treatment has been correlated with reduced levels of these abnormal protein aggregates, the plaques and tangles associated with pathologies.
So it might not just be a growth factor promoter, but an environmental cleaner as well. It's making the brain a healthier, cleaner place to operate.
That's the idea. It's a powerful combination, promoting new, healthy connections while simultaneously helping to clean up the toxic residue that can hinder the existing ones.
That is a powerful 1-2 punch.
Yeah.
Okay, so what is the fourth and final pathway that P21 is hypothesized to influence?
The fourth action focuses on the absolute mechanics of information transfer. It's about improving synaptic plasticity. As you said, synapses are those tiny gaps where neurons communicate, and plasticity is the ability of those communication lines to strengthen or weaken based on experience. It's the core process of learning. P21 has been shown in these studies to increase the expression of proteins that are vital for synaptic function. Two of the big ones are called synaptophysin and postsynaptic density protein 95, or PSD 95.
And what do those proteins do, in simple terms?
You can think of them as the physical infrastructure of the synapse. They are like the nuts and bolts and docking stations that allow the electrical signal to jump that gap efficiently and reliably. Increasing those proteins means the transmission of information is faster, more robust, and more durable.
The signal is stronger and clearer.
Exactly. And the research specifically notes that this strengthening of the synaptic architecture is what correlates directly with the behavioral improvements they see in the animal studies, like that enhanced performance in complex learning tasks. So we're talking about observable, measurable increases in cognitive capacity in non-human subjects.
Let's put a finer point on those cognitive effects. Beyond just navigating a menu is better, what other specific observable improvements in learning and memory are cited in the source material for these P21 or P021 treated animals?
Well, researchers often use a battery of tests to look at different aspects of memory. In addition to spatial memory, which is the water maze, they see improvements in fear conditioning tests.
Which measures what exactly?
That measures associative learning and emotional memory. And interestingly, treated animals show improved extinction of fear responses. This suggests a better ability to update and reorganize existing memory pathways to learn that something is no longer a threat. It's a sign of a more flexible, adaptive brain.
That's a really subtle but important point. It's not just about learning, it's about unlearning too.
It is. Furthermore, in object recognition tasks, which test short-term working memory, they show a significant retention advantage over the control groups. The data, taken as a whole, consistently points towards not just the maintenance of existing neural systems, but an active acceleration of adaptive learning and memory consolidation processes.
Okay, that paints a really holistic picture. So to summarize this whole section, the research suggests P21 is a robust brain growth supporter because it's hitting these four major targets at the same time. It's protecting the old neurons, it's turning off the natural brake signal, LIF, to promote new neurons, it's supercharging the whole environment with BDNF, and it's physically strengthening the connections required for communication, all of which shows tremendous potential.
Again, confined entirely to preclinical models. That is the essential summary of the research excitement, yes.
All right, so now let's pivot. We've talked about what P21 does. Now let's talk about how researchers actually get this fragile little peptide into the system to observe these incredible effects. It's almost universally used as a nasal spray, not a pill. We touched on the digestive challenge, but let's dive deeper into why the intranasal route is the researchers' preferred shortcut.
The digestive challenge for any peptide really can't be overstated. As we discussed, these are just short chains of amino acids, the same building blocks as protein. Taking P21 orally would be a complete biochemical failure. Stomach acid and protease enzymes in the gut would just dismantle it into individual amino acids before it could ever be absorbed intact.
So it would just be like eating a tiny, tiny bit of chicken, no therapeutic effect.
Essentially, yes. So, to ensure the active, intact peptide reaches the systemic circulation, and ideally the central nervous system, researchers have to find a way to bypass the entire gastrointestinal and hepatic system. The liver, too.
Okay, so a pill is out, but why not just a simple injection? Under the skin or into the muscle? That's pretty common for other peptides.
It is, and while injections do bypass the gut, they still rely on systemic circulation and then have to face the final boss, the blood-brain barrier. And while P21 is small, the BBB is incredibly restrictive. It actively limits the passage of even small molecules to maintain the brain's very isolated, stable environment. The real beauty of the intranasal delivery route is that it offers a potential direct route to the brain, completely sidestepping the BBB's most formidable defenses.
That sounds like a true game changer for neurological research. Let's detail the 4 key reasons the sources give for using this specific delivery method for P21.
The first, and by far the most compelling, is that direct route to the brain. The nasal cavity isn't just a tube for air. The upper nasal passages, an area called the olfactory region, house the terminal endings of the olfactory and trigeminal nerves.
The nerves for smell and facial sensation.
Exactly. And these nerves connect almost directly from the nasal epithelium, the lining of your nose, right into the central nervous system. So When a small lipid-soluble molecule like P21 is atomized and sprayed onto the surface, it can potentially be taken up along these nerve dendrils.
It just travels up the nerve itself.
It's believed to travel along the nerve sheaths, yes, into the cerebrospinal fluid and the brain parenchyma itself.
So it's like using the telephone wires that are already installed in the house to sneak a package inside, rather than trying to bust through the concrete front wall.
That's a perfect way to put it. This is often referred to as nose-to-brain delivery. And this theoretical pathway allows the active peptide to reach targeted regions of the brain, like the hippocampus and olfactory bulb, much faster and in potentially much higher concentrations than if it relied solely on diffusion across the blood-brain barrier after floating around in the general circulation.
Wow. Okay, what's the second advantage? You mentioned metabolic efficiency.
Right. The second advantage is that it bypasses first-pass metabolism. When any compound is absorbed orally, the very first place the blood goes after leaving the gut is directly to the liver. This is called the first pass. And the liver is the body's primary detoxifier and metabolizer.
And it's brutal on fragile molecules.
Extremely. For delicate peptides, first-pass metabolism in the liver can destroy up to 90% or even more of the active compound before it ever reaches the rest of the body. Intranasal delivery completely skips that entire liver processing step.
Which result in much higher bioavailability.
Vastly superior bioavailability. Much more of the active, intact peptide actually gets to the intended destination.
So you get better efficiency and a higher concentration past the primary defenses. That has to make the research more reliable and maybe lets you use lower, safer doses.
It does. Which leads to the third advantage, which is all about the practicalities in a research setting. It is non-invasive. Compared to repeated injections or much more complicated and risky delivery methods like an intrathecal injection directly into the spinal fluid, a simple nasal spray is incredibly convenient and humane. This eliminates the stress and the physical trauma associated with invasive procedures, which is a huge benefit whether you are testing on animals or, one day, trying to develop a future human therapeutic. It's simple, it's painless, and it's highly reproducible.
And what about that reproducibility? The need for experimental integrity, for consistency.
That is the fourth and final advantage: precise dosing. When administered correctly, using specialized atomizers, the actual spray devices, the intranasal route allows researchers to deliver a very precise, very consistent volume and concentration of the solution with every single actuation of the pump.
No guesswork.
No guesswork. For an experiment where you are trying to quantify a biological effect, knowing exactly how much active compound you're administering, dose after dose, subject after subject, is absolutely essential for the data to be valid. Oral delivery or even certain injection types can be prone to much more variability.
So the intranasal route is fundamentally tied to P21's successful application in a research environment. It's like the necessary technological bridge between this fragile molecule and a very difficult-to-reach target site.
That's a very succinct summary. For compounds like P21, the delivery mechanism is often 50% of the research battle.
Okay. Now we come to the most critical pivot point in this entire discussion. This is the part that any learner engaging with this material has to fully grasp: the legal, the regulatory, and the safety status of P21. We have emphasized its experimental nature, but now let's dive into the really sobering realities of that classification. So what does this all mean for this compound status in the wider world?
This is where we shift gears from exciting biological potential to stringent and necessary regulatory reality. The foundational knowledge gap here is absolute and cannot be overstated. P21 has not been tested in humans through formal clinical studies. No phase 1, no phase 2, no phase 3. It exists purely in the realm of in vitro cell culture and in vivo animal investigation.
And the implication of that lack of human testing is it's just a massive expanse of unknowns. We have no idea what the human metabolic profile is, what the long-term safety looks like, or even what an effective dose would be.
Precisely. There is no established safe human dosage. There's no established dosing frequency. Nor is there a confirmed human metabolic or toxicological profile. The human body might process this compound in a way that is completely different from a rodent. It might break P21 down into toxic metabolites that don't appear in mice, or it might clear it from the system so quickly that it has absolutely no therapeutic effect. These are fundamental life-or-death questions that remain completely unanswered.
Let's review the findings on animal safety then, since those sources provide the only safety baseline we have. Were there any major red flags in the preclinical data from the animal studies?
The animal data is, thankfully, the basis for the continued enthusiasm because it does show encouraging tolerance. In the longer-term rodent studies using the precursor P021 and in the shorter P21 studies, researchers generally found good tolerance at the experimental doses they were using.
Good tolerance meaning what, specifically?
Specifically, they found no major toxic effects on liver or kidney function tests. The animals showed stable behavior, no unusual changes in their weight or their appetite, no overt signs of neurotoxicity or organ damage, and, importantly, no evidence of tumor formation was reported in the available literature.
That's a big one.
It is. In fact, some studies even noted what you might call a beneficial side effect, observing reduced anxiety-like behavior in the treated subjects compared to controls.
That's all reassuring for a lab environment, but it's still operating on the massive premise that a rat or a mouse is a perfect proxy for a human being.
And we know from decades of medical research that that is rarely the case, particularly in neuroscience. For example, the lifespan of a laboratory rodent is vastly shorter than a human's. What appears benign over a 6-month period in a mouse could manifest as a very serious chronic condition or a slow-building toxicity after 10 or 20 years in a human. So, good tolerance in an animal model offers absolutely zero guarantee of safety or efficacy in humans. It's just a green light to continue researching, that's all.
Okay, given P21's potent mechanism of action, forcing neurogenesis, upregulating metabolism, what are the theoretical side effects that researchers would have to be vigilant about?
Based on the mechanisms, researchers primarily identify two main theoretical risk areas. First, because of all that increased activity, the forced neurogenesis, the synaptogenesis, the overall enhanced plasticity, the brain is going to demand a significant amount of energy.
It's working overtime.
It's working overtime. P21's action could result in increased metabolic demands on the brain and the body. So researchers theorize that this might lead to things like generalized mild fatigue or subtle changes in energy levels, particularly during periods where the brain is actively repairing or adapting.
It's the cost of doing business. The brain is working harder, so the body might feel tired. Makes sense.
Exactly. The second theoretical risk is much more mundane, and it's related to the delivery method itself. As with any compound that's delivered intranasally over a long period, there is a potential risk of localized irritation, nasal dryness, or minor damage to the nasal mucosa from repeated exposure. Although, to be clear, there is no specific public data detailing this risk for P21 in particular.
All right, let's move to the supply chain and the regulation. This is perhaps the most crucial public safety message here. How does P21 exist legally, and what is the danger of its unregulated status?
P21 is strictly an experimental compound. Therefore, it is unregulated by major pharmaceutical administration bodies, the FDA, the EMA, any of them, for any kind of therapeutic or supplement use. This isn't a slight distinction. It is the fundamental difference between a controlled, verified medicine and an unverified chemical from a lab.
And what does being unregulated practically mean for someone who might, for whatever reason, try to buy this compound?
It means that the purity and the concentration of the product can, and often do, vary dramatically from one supplier to the next. When you buy an approved medication from a pharmacy, you know that the regulatory body has inspected the manufacturer and guarantees the chemical identity, the purity, usually 99.9% or higher, and the stated concentration in the pill or solution.
But with an unregulated research chemical, you have none of that oversight.
Yeah, you have zero oversight. You are relying 100% on the integrity and the quality control of a specialized research chemical supplier, which can be variable. The dangers are threefold. First, the compound may be significantly less pure than advertised. It could contain residual solvents from the synthesis process or other impurities that could be toxic or reactive.
Okay, so purity's one.
Second, the stated concentration might be completely inaccurate. This is a huge one. A researcher or a non-researcher might think they're administering 1 milligram, but they could actually be administering 5 milligrams or 0.1 milligrams. This makes any kind of controlled use impossible and potentially very dangerous.
And the third danger, which sounds like the most alarming,
misidentification. The most serious risk is that the compound being sold as P21 might not be P21 at all. In the absence of regulatory checks and independent testing, less scrupulous suppliers could sell a cheaper, non-functional peptide, or worse, a completely different and potentially harmful chemical altogether. Legitimate pharmaceutical manufacturing is one of the most highly regulated industries in the world precisely to prevent these kinds of life-threatening errors.
that really emphasizes why the supply chain itself is so dangerous for anyone even considering this outside of a verified, controlled lab setting where they can do their own independent quality checks. So where is it legally sold?
It is sold exclusively through specialized research chemical vendors. These are companies that cater specifically to universities, pharmacological labs, and independent researchers. It is not available in pharmacies, it is not in drugstores, and it is not approved as a dietary supplement or a medical therapy anywhere. The entire basis of the sale is on the premise of non-human application.
And the labeling. The labeling is the ultimate warning sign for anyone who might encounter it.
Absolutely. The crucial warning must be present on the product. Legitimate suppliers adhere to strict ethical and legal guidelines. They must clearly and prominently label P21 with the words, "For research use only, not for human consumption."
And they often make you agree to that.
They do. The purchase process often requires the buyer to tick a box or sign a disclaimer confirming that they are purchasing the substance exclusively for laboratory or non-human research purposes. This explicitly acknowledges the serious legal and safety distinctions and shifts liability.
So that confirmation process exists to underscore these strict boundaries.
Yeah.
Anyone who purchases this, knowing that label and signing that confirmation, is knowingly stepping outside the entire established medical and consumer safety framework.
That is the definitive regulatory reality. The integrity of that research chemical boundary is paramount to the entire system of drug development and public safety.
This deep dive has provided an incredibly detailed look at a compound that is truly at the absolute forefront of neurotrophic research. It really represents the potential of target engineering to overcome the limitations of our own natural growth factors. Before we close out, could you give us a final synthesized summary of P21?
Certainly. P21 is best characterized as a highly promising neurotrophic research peptide. It's an engineered small molecule fragment that's derived from the powerful natural growth factor, CNTF. It was specifically designed to bypass the physical and immunological limitations of that full protein. And preclinical research suggests it is a powerful modulator of brain repair and plasticity, primarily through a triple action mechanism, boosting BDNF levels, strengthening synaptic connections, and most uniquely, promoting neurogenesis by blocking the brain's own natural inhibitory signal, LIF.
And the practical reality for you, our listener, following this cutting-edge science, is really the critical dual nature of P21. On one hand, you have immense theoretical potential, suggesting a new era of brain repair might be possible. But that is balanced by the rigorous caution required because it remains entirely unapproved, structurally unverified in human trials, and subject to all the hazards of a completely unregulated supply chain.
We have to reinforce that distinction. The science is incredibly exciting, but the regulatory status demands absolute prudence and the recognition that this is a research tool, not a consumer product.
Now, let's leave you with a final provocative thought, building on what we learned about P21's most unique mechanism. Its ability to inhibit LIF, that natural brake signal on new neuron growth.
That ability to manipulate a biological inhibitor, that's where so much of the future research focus lies.
It raises a really profound question about our own evolution and future therapeutic design. If research can, in fact, successfully isolate and temporarily remove these natural biological brakes, what does this imply about the adult brain's inherent, maybe latent, capacity for self-repair?
It suggests the potential is already there.
It suggests that the brain might, by its very nature, be primed for far greater healing and regeneration than we currently experience. But that these existing evolutionarily protective regulatory systems, like LIF, are in place to prevent it from running too fast or too hot, prioritizing that long-term stability.
So future therapeutic design may increasingly focus not just on introducing novel compounds to force growth, but on carefully and temporarily removing those pre-existing stabilizing limitations that the body built in to ensure a long-term slow equilibrium. P21, even in its research infancy, offers this vivid demonstration of how manipulating that natural check and balance system might unlock an unprecedented capacity for self-repair.
P21, in its current research status, serves as an early blueprint for how we might one day unlock that dormant regenerative potential, simply by learning how to temporarily turn off the natural stop sign. And that is a truly fascinating pathway for future research to explore.
A powerful thought to end on.
And on that note, we must reiterate that all of the discussion here was strictly for educational and research purposes only, drawing only from the preclinical source material provided. We encourage you to review the original research for yourself and to follow the development of neurotrophic peptides responsibly.
Thank you for joining us for this deep dive into P21 research.
We'll catch you next time for more deep dives into the science that is shaping our world.